Okay, so I would like to start by introducing Axelera AI. We started the company 3.5 years ago with a good dozen of people on board. At this moment in time, we are approaching 200 employees spread out across the globe. Most of it is in Europe. We have our headquarters in the Netherlands, but also offices in Belgium, in Leuven, in Zurich, Milan, Firenze, in Bristol, Paris, Germany, and in Greece and Romania, and people in the US and in Taiwan. But we do more than just opening offices. We also have a product now developed, and that is an AI platform. It consists of both the hardware and the software, and the software allows you to easily deploy deep neural networks, so AI algorithms, on our hardware. We are heavily venture-backed by private equity funds, but also by governments. We have now raised over $110 million, and we have our first product ready. It's now in the hands of our customers. They're providing us with feedback, and by the end of the year, we go to mass production and general availability. And what we really want to do is to bring AI to everywhere. AI should become the new electricity. It should be part of any of the devices that we're using today. And very importantly, we would like to democratize AI. So we would like to lower the threshold so that everyone can really use AI, as this is a very powerful tool. And what we believe is that in order to do so, we have to bring AI towards the edge. And then the question, of course, arises, what is exactly the edge? So the edge is best explained by contrasting edge AI with cloud processing and cloud AI. Now, in the cloud AI, you have all your devices. This can be mobile phones, cameras, drones, other devices. They're all connected through a network connection to the cloud. In the cloud, you have large server farms, and actually all the significant processing is being done inside the cloud, and the result is being sent back towards the devices. So you send your information first towards the cloud, and you get your result back. In the context of AI, so cloud AI, this means you send your data towards the cloud, you do your AI algorithm processing there, and you get the result back. Now, this has a lot of advantages. In the cloud, you can scale easily. You're very elastic in terms of the compute, the memory, the storage that you have available. And that also allows you to run the largest AI models that are currently available. Think about GPT-4, for example, that you probably use regularly. Now, it has a lot of advantages, but also significant disadvantages. So, because you have all this abundance of compute available, often it's not very energy efficient. And also you require a network connection, you require significant bandwidth. You have to make sure that the costs don't explode. And there's, of course, the concerns of data privacy. You're sending your data towards the cloud, so you're not sure what is really happening there with your data. So this is where then really edge AI can come in. It can solve some of those problems that cloud AI has. And with edge AI, you are not computing inside the cloud, so through a network connection, but you're actually computing near the device of interest yourself. So you have a device, this can be the mobile phones, the cameras, the drones, and so on, and you're computing either inside the device or near the device. So you see already, it's not a super clear definition of what edge AI now is, and often one distinguishes between different kind of layers of edge computing. So on the bottom, you can see the more IoT layer, which is really the layer where you have your small end devices, your endpoints, and you're computing really inside of it. So you have very small chips there available. Now, above that, you have the thin edge. So in this, we are in a network environment, and we have these gateways, we have routers, switches, and so on. And these devices can also be used to perform AI compute, because they get a lot of data in. And above that, you're more at the thick edge. Here is actually the edge servers, for example. You have your on-premise servers that are doing all the AI compute. Again, you're not going towards the clouds. These are servers, but not in the cloud. You are computing near the devices that are connected to these edge servers. So this is edge AI. You do your compute there, and some examples. There are lots of industrial verticals that make use already of this edge AI. So this is a nice example here. It's a company called Seagate. They are using this for retail purposes. They have this kiosk with a camera on top of it, and whenever there's the self-scan, the self-checkout in a shop, they register what is the customer actually using and scanning and putting into their bag. They're using the computer vision algorithms for that, segmentation, object detection, and so on. And in this way, they can be very secure in the type of checkouts that are being done. Another type of application is more industrial. You have this robot that can pick up certain objects and place them in the right position. Also here, this is based on computer vision with a camera related to it. We have an edge server near to it that can accumulate all the data streams from the various cameras that are out there for the different kind of robots. And again, segmentation, object detection, all these kind of algorithms are being used. But it's more than just these two applications, of course. It's also in terms of security, mass surveillance kind of applications where you have, maybe in these kind of buildings, all the cameras out here. You would like to process those streams to detect some important events in an automated way. And also here, Edge AI can really help out. Agricultural applications where you have to have pest control in an automated way. You want to inspect your crops, for example. Also here we have customers that are actually looking at Edge AI as a solution. And then finally, healthcare. If you want to have real-time patient analytics or the data coming in from different kind of devices worn by the patient, here Edge AI is well suited. Now, what are the advantages of Edge AI? Now, because we don't have this connection towards the cloud anymore, we are much more reliable. We can also have a lower latency in our response because we don't need to go there anymore. Also, we have data privacy that is much better. We are near the devices. We keep the data near the devices. They are not sent towards the cloud. There is also the cost that go down. And we have, in many cases, better security there. So these are the advantages, but it's not all positive. When you go towards the edge, you are usually in this really resource-constrained environment. There's not an abundance of compute resources or storage resources anymore. So you have to really start to deal with that. How can you deal with just limited processing power, with limited memory, limited storage, and energy that is available for you? Often the budgets are also smaller. You need to make sure that the data that you store on those edge devices are secure, that they cannot be tampered with. And there are also some cooling constraints. And all these constraints, they're really important because if you look at the recent trends in the AI models out there, you see that the sizes of these models are becoming exponentially larger. Back in the 90s, we were still at very small models. These were like hundreds to 1,000, maybe 10,000 of parameters. If you now go to the largest models, the biggest models that are out there, these are in the trillions of parameters. And if you want to have powerful compute at the edge, where you can do similar things to what these very large models can do, you have to make sure that you manage your resources really well and that you also keep energy consumption in check. So how can we solve this? How is it possible? How can we bring powerful models towards the edge? I think you can do this in two ways. On the one side, you can improve your hardware, and on the other side, you can improve your software. And I will discuss some examples of how to do this for both of these possibilities. So let's first talk about the hardware. So the hardware, there are a range of devices that can be used for Edge AI. On the one side here, on the left side, we have the CPU, which is for most general compute. This can be done for any type of task at hand. It's really built to be general purpose. I'm thinking about the Intel Core, Intel Atom, Intel Celeron. These are type of CPUs that are often used towards the edge. But yeah, they're really general, but they're not very powerful and fast, especially for edge AI. If you then move towards the right side, you pass towards a GPU. GPU was originally made for graphical purposes, but all the parallel processing that was needed for those to analyze all those images turns also out to be very good for AI algorithms. So the GPU is a very popular kind of device for AI. Then if you move further towards the right, you pass the FPGA, which is more specialized, and eventually you arrive at the ASIC, which is an application-specific integrated circuit. So with the ASIC, the target is really one particular application. It's application-specific. And in this case, it's targeting AI algorithms. Because you are targeting only one certain type of compute, the compute that is necessary for these deep neural networks that are currently very popular in AI, you are becoming more and more specific. You're becoming more and more powerful for just that type of compute. So that's a big benefit. On the other hand, because you're really focusing on one type of compute, you are not that general anymore. You lose some of the flexibility that you, for example, had with the CPU. The CPU is made for any type of compute, while the ASIC for just a specific compute. Now, the big benefit of AI algorithms is that despite the fact that they are based on very limited kind of computations that are being done, and I'll explain later on which computations those are, they are still, when you bring all of those computations together, they arise and they build up something that is very general, that is artificial intelligence. And you can see this trend that we're moving more and more towards something that is able to do many types of tasks, is becoming more and more general in its intelligence. So we have very limited compute, well, very limited kind of operations that we need to support, but when we bring all of that together, it's supporting something very general. So I think that is a very powerful aspect of today's AI. So I've mentioned that compute. So what is that compute? Now, the compute is all based on matrix vector multiplications. And that sounds very fancy and maybe even complicated, but it actually isn't. It's just a matter of multiplications and additions that are being done. And you can see that on the output array here on the right side. It's just you multiply a couple of numbers and you add them. And turns out that in over 90% of the cases in such an AI algorithm, a deep neural network, they are just these kind of matrix vector multiplications, just these multiplications and these additions. So the goal is then to really focus on this kind of compute. If you are very good at solving matrix vector multiplications, you can be very good at running AI algorithms. And turns out that you can do a lot of those matrix vector multiplications in parallel. In fact, each of those rows here in the output, there are 3 rows here, they can be done in parallel. And that's why the GPU, for example, is a very good device for this. A GPU is made to do all these parallel computations. And because it was made to do that, it could also do these matrix vector multiplications in parallel and is therefore a very efficient tool. So we have these matrix vector multiplications that we would like to speed up and be very efficient at. There's one more thing that we also want to do, and that is being efficient at memory transfers. So in a typical compute architecture, which is called von Neumann architecture, there is the processing unit, and you have the memory, here the RAM, memory and RAM. Memory, RAM, and the processing unit. Now, what happens when you want to do some compute is you fetch data from the memory towards the processing unit, and do your compute, and you write it back towards the memory. And that is typical von Neumann architecture, and that is abundant in most of the computers that we are using today. But the problem is that by fetching data from memory, it takes first a lot of time, and it's also very energy intensive. You waste a lot of energy there. So in some sense, what we want to do also in AI, because AI is very data intensive, right? There's a lot of data that needs to be processed. We want to make sure that we also are very efficient in fetching those data, in dealing with the memory processing there. We want to solve the von Neumann bottleneck. Now, so we have two things that we want to do. Be efficient at the matrix vector multiplications and being very efficient at the memory transfers. And there are many ways of making these more efficient. I will explain here one of them, and that is using large arrays of in-memory computations. So let's split this up into first the large arrays and then the in-memory computations. So when we're talking about large arrays, it means that we have a lot of data coming in from the left side. This is they can all come in parallel. Then we have in the center, we have these blue boxes. These are all compute units. What they do is they do these multiplications and these additions from the matrix vector multiplications that I mentioned earlier. So they can do all these compute units, they can work in parallel, so that at the bottom, we are getting a lot of solutions, a lot of output simultaneously out. So that is these are those rows in those matrix vector multiplications from earlier. So what we now have is an array that can do all these multiplications and those additions simultaneously for a lot of input data, resulting in a lot of output data. A lot of data coming in, a lot of data coming out. So that's one thing. Now we're efficient at these matrix vector multiplications. We can do them fast in parallel. Now the other thing is we want to be efficient at the memory transfers. And what we do is we compute inside the memory itself. So instead of fetching from an outside memory towards a processing unit, we have a processing unit inside the memory. So we don't waste that time anymore of fetching from outside, and we can immediately do the processing. We are energy efficient because we also don't have to fetch from far anymore. So this is the second kind of solution that I propose over here. And it's maybe important to note that the in-memory computation, you can do this in two ways. There's the analog way, which can be incredibly energy efficient, but you lose quite a bit of accuracy there if you have a solution. So it's harder to commercialize. And you can do it also in a digital way. In a digital way, it's still energy efficient, but it's much more accurate. You don't have all the noise that comes from these analog devices. And it's much easier to scale with the node technology that we have, the node scaling that we have ongoing. So we have now the solution, well, a solution for efficient matrix vector multiplications and the memory transfers. So that is the hardware side of a solution. On the other hand, I was mentioned also that there is a software side. You can also improve a lot there, and those are often the simpler, the easier solutions to get to a viable solution. So one part of the software optimization is optimizing the algorithms themselves. And what these optimizations all target is a better throughput, less memory usage, less storage, more energy efficiency, while maintaining the high accuracy that you have in these algorithms. And you can do this in various ways. One of them is using quantization, for example. The typical kind of AI algorithms, the deep learning algorithms, they use floating point data points with 32 bits in size. Now, because there are 32 bits, it means that you have to fetch 32 bits from memory each time for each data value and do a processing on 32 bits, which is a lot of compute. But what turns out to be true is that in many cases, you can actually work with much lower precision. For example, you can work with 8-bit data and integer data types, which is much more easy to work with. So by doing so, you reduce the memory bandwidth needed. You're much more efficient at it. Your processing becomes better, and you also have smaller models, so less storage is needed. Another solution is using pruning. These AI models these days, they're huge. They're really large. But turns out that you don't need all those parameters. You can actually get rid of quite a bit of it, and still the algorithm will work very well and be very accurate. And that is called pruning. You move away some of the parameters. And then finally, you can optimize your AI algorithm itself, your architecture of your network. For example, they can be much smaller. You can have much more efficient processing nodes in between. And you can even optimize for the particular hardware that you are using. And an example of this is shown over here. So a couple of years ago, we had this model called Palm Coder, which was a neural network designed really for programming. So it's really for programming task, it was doing really well. But it used over 500 billion of parameters. Now, just 1.5 years later, and actually right today there are even better models available, we have a model called Phi-1, which is only 1.5 billion parameters large. So we have decreased the size of the model by 2 orders of magnitude. And actually, when you look at the green curve, you can see that the accuracy of this model, so the programming ability of this model, actually increased. So this is, of course, great news for the edge. Now we have a much smaller model that we can deploy with our limited resources that we have. And it is also very accurate in its abilities. And the reason why this is possible is because we have more data, we have more reliable data, we have also better training techniques, and so on. So these are the algorithm optimization techniques that are available. You can also do a lot in the compiler itself. I'm not going to go into details there. It's very hardware architecture specific, but some of the examples are operator fusion, where you bring 2 operators together so that you don't have to do the 2 computes anymore. You can have very efficient memory mapping, and depth first processing is also one. But the most important thing is that if you really want to be as efficient as possible, then you want to bring the hardware development and the software development together. You develop your hardware with the software already in mind, and the software you adapt as well as possible to the hardware principles that you're using while developing it. That's when you get really the best solution. So this is some strategy to bring AI to the edge in a very efficient way. But if you look at, and if remember that we want to bring AI to all the devices and to democratize it really, but if you look at today's solutions that are out there, then like the FPGA, the GPU, the CPU, and so on, they are usually good at some dimensions, like cost, performance, or energy efficiency. But they're rarely good at all the dimensions. And we would like to have all of that if you want to bring AI towards all devices and make the threshold for using it very low. So, and that's where we have developed our product. We call it, the chip itself is Metis, is our first generation chip. It uses this digital in-memory computation, and we have brought it towards different kind of solutions. This can be like modules, like M.2 module, but can also be PCIe cards. We are working on a single board computer, and we also have real AI PCs ready. So these are PCs ready together with our partners Dell, Lenovo, Advantech, and so on. So these are our hardware solutions, but on top of that we also have a software solution, which is our Voyager SDK, which allows you to easily deploy these deep neural networks on our hardware, and that in a very efficient way. So we take care of a lot of the optimizations that are needed to do this in an efficient way. So, and if you then compare this solution to solutions that are out there, like the NVIDIA GPUs, we tend to be at similar performance as the NVIDIA GPU, like the AGX Orange, for example, really the higher level edge devices. But on the other hand, we are much more energy efficient, 50% more. And in terms of cost, we are at least 2.5 times, doing 2.5 times better. And if we compare our solutions towards other edge solutions from other startups out there, we are doing better in terms of compute itself, the throughput, but also in terms of energy efficiency and in terms of the cost effectiveness. So this is one of the examples that we have made here. I want to show you for a surveillance type of applications. We have these 24 RTSP cameras that are all feeding in to a single Metis chip, and they're processing this with computer vision algorithms to do object detection, segmentation, and so on. And the nice thing is that all those 24 cameras, they can be processed by one chip. And actually, we can have more cameras if we want to. So you can imagine that for a surveillance kind of applications, this is really beneficial. Usually, it's about the cost per stream that they're looking at. And if you have many streams being processed by just a single chip, that is a major benefit. So that was my story about bringing AI towards the edge. If you have any questions, I will be here for a little bit longer. I would love to go into a discussion with you or answer your questions. Thanks a lot.